talk about vertical asymptotes of rational functions. And I'm going to start with a basic one that you've already seen. Let's start with f of x equals 1 over x. And if you recall, this particular function has a graph that looks like this. All right, a branch of the hyperbola that goes here, and a branch of the hyperbola that goes here. There are two asymptotes for this particular function. One is this vertical asymptote right here at x equals 0, and another one that's horizontal at y equals 0. I'll talk about horizontal asymptotes on another video. We're going to focus on vertical asymptotes. So the vertical asymptote for this particular function was at x equals, x equals 0. The y-axis has this as its equation. Now we know that if we change the function and make it look like this, f of x equals 1 over x minus 3, that it has been shifted to the right 3 units. So we take this particular picture, pick it up and shift it right, and now our function would look like, or our graph would look like this. We'll have a vertical asymptote right here at 3. And we would draw the exact same shape right here. And it looks something like that. So our vertical asymptote is at x equals 3. Now I want to point out a couple of things. One is this x equals 3 comes from the number that would make the denominator 0. So if we look at a rational function, and by the way, I didn't even define that for you. A rational function is a function where you have a polynomial over a polynomial. Our vertical asymptotes come from the numbers that make the denominator 0. But let me also remind you of why we have vertical asymptotes there. If you were to plot a few points, and I mean put in x values that are close to 3, close to that number that would make the denominator 0. For example, if I put 3.1 in, you could grab a calculator and do the calculation. If you put 3.1 in, you would find that the y value is 10. So at 3.1, I would be way up at 10. You get closer, put in 3.01, pop that in, you would find you're at 100. And the closer you get to 3, the higher the value. That's why we have a vertical asymptote. Similarly, to the left of 3, like if you put in 2.9 and did the same kind of calculation, put 2.9 right in here, you would end up with negative 10. At 2.99, pop that number in, you'll find that you'd get negative 100. So the graph is heading off and approaching this line from both the right and from the left. Let's keep going. Using this idea that the vertical asymptote comes from when the denominator equals 0. Here's our next problem. Let's find the vertical asymptotes for f of x equals x plus 11 over x squared minus 3x minus 28. Now to find where the denominator equals 0 here, I'm going to factor. So the function would look like this. X plus 11 over, let's see, it's just our traditional factoring for a trinomial. I'd have x and x. I'm going to break up the 28 into 7 and 4. I need a negative 3 in the middle, so that means the 7 is negative, the 4 is positive. So our rational function now looks like this. But our vertical asymptotes come from numbers that make the denominator 0. So our vertical asymptotes for this particular problem would be x equals 7 and x equals negative 4. And it's done. We're not going to graph it right now, but I just wanted you to see how we get that vertical asymptote. Let's do another one. How about g of x equals x cubed plus 2 over 5x squared minus 11x. Again, our goal is to find the vertical asymptotes. And again, I'm focused on this denominator. Notice this time to factor, we can see there's a common factor of x, so let's take that out. In the numerator, we still have x cubed plus 2. In the denominator, now I have x times 5x minus 11. But again, our vertical asymptotes come from the numbers that make the denominator 0. So we have this x here. That means the vertical asymptote would be at x equals 0. And the number that makes 5x minus 11 equal to 0 would be x equals 11/5. Our vertical asymptotes don't have to occur at integer values, right? 11/5 is, what is that, 2.2 if you change it to a decimal? Totally fine to have vertical asymptotes there. Let's do another one. Let's look at the function f of x equals 8x squared minus 3 over x squared minus 7. Now this one doesn't factor with respect to the integers, but we do know we could just set x squared minus 7 equal to 0 and find the solutions to this equation. I could add 7, take the square root of both sides, don't forget to put the plus or minus in. So the numbers that make this denominator 0 are positive square root of 7 and negative square root of 7. So those are in fact the places for our vertical asymptotes. There will be one at positive square root of 7 and a vertical asymptote at negative square root of 7. So again, now we see that the vertical asymptotes don't even have to occur at the rational values. These are irrational numbers, but that's totally fine. Let's look at this next one. G of x equals x plus 6 over x squared plus 4. If we treat this one the way we did the previous one, it's not factorable with respect to the integers, but we'll still set the denominator equal to 0 and solve. When we take the square root of both sides here, notice we're taking the square root of a negative number. So the solutions are plus or minus 2i. So in this case, there are no vertical asymptotes because we do require that those values be real, and those are not. So with respect to the vertical asymptotes, I would just say there are none. So if we were to look at the graph of this particular function, there would be no vertical asymptotes. Let's do one more. Let's look at f of x equals x plus 3 over x squared plus x minus 6. Our goal is still the same. How do you find the vertical asymptote? So we're going to factor the denominator. This one is factorable with respect to the integers. So we have an x and an x. Let's see, 6 is either 1 and 6 or 3 and 2. 3 and 2 will give us that value. In the middle, a positive 1 in the middle if we put a plus here and a minus here. Now initially you might think, hey, well, you have a vertical asymptote at -3 and +2. But this problem has an extra little wrinkle, and here it is. This factor of x plus 3 also exists in the numerator. If you look back at any of the other examples I gave you, that was not the case in any of them. So this is actually something that you have to double check. When you have a factor in the denominator, you have to look at whether the same factor is also in the numerator. So here's what we would do. cancel your x plus 3's. So the new function looks like this. F of x equals 1 over x minus 2. But we still know that x can't be negative 3. So this function is equivalent to 1 over x minus 2, where x doesn't equal negative 3. So the vertical asymptote only occurs here at x equals 2. Now, what is happening at x equals negative 3? Let me show you. We know what this graph looks like. It has a vertical asymptote here at 2. Has a horizontal asymptote here at 0. Remember, it's our graph y equals 1 over x that's been shifted right to 2. So our graph would look like this. But here comes a little wrinkle. Right here at negative 3, we'd say there's a hole. There's just one point where the graph doesn't exist. Right here at negative 3. Here's my value at negative 3. So as I graph this branch of the hyperbola, over here at negative 3, you actually skip over that point. So that's the extra little wrinkle you have to consider when you're finding your vertical asymptotes.